gentlemen, welcome to Science and Nature Are Bigger Than Us. 6 Memos for Humankind. This is the last evening of the Italian Space and Science Festival, organized by the Italian General Consulate in Frankfurt and the ESOC-EUMETSAT Italian Culture Club. My name is Paolo FERRI. Tonight we'll take you to a long journey in space and time, and we begin with the origin of the solar system in the depth of space. So picture yourself in the very far, very distant time. Talking about 4.5 billion years ago. That time the universe was already almost 10 billion years old. Our galaxy was already formed, more or less in the shape that we know it today. But our solar system didn't exist. In some remote corner of the galaxy, actually peripheric corner, we are still in the periphery of the galaxy. A huge cloud of dust and gas existed. And this cloud probably existed for billions of years, until one day a star, maybe a nearby star, exploded, a supernova, and the pressure wave initiated a process that would end up with the creation of the solar system. This process was a collapse, gravitational collapse of the cloud into its center. Under its weight, it kept increasing the pressure, and at a certain point in the center of the cloud, the pressure was so high that the forces induced by the pressure of the gravitation overcame the forces of the nuclear, of the atoms inside the nucleus of the gas. And this meant that nuclear fusion started. It was the ignition of the sun. It was the birth of the sun. In the meantime, around the sun, the cloud still existed, and it rotated faster, because by collapse it was getting smaller and it was increasing its rotation. The matter that didn't form the sun started to create small corps, small bodies, and these bodies, by gravitational accretion, became bigger and bigger, accumulating the dust and the gas that was around them, rotating around the sun. This was the formation of the planets. It took only a couple of 100 million years to form the planets, so the solar system was still very, very young at that time. The big planets, rocky towards the sun, and more, say, less dense and made of liquids and gas going away from the sun. Then there was something that was remaining. All the matter, all the gas and dust that remained from the formation of the planets, it was swept to the periphery of the solar system, very far away. We're talking about billions of kilometers, but in fact even larger distances. We believe this matter exists unto interstellar distances from the sun. This matter remained there, preserved forever, for all the billions of years that the sun and the solar system existed, until our days today. Today we observe something that happens occasionally, in fact very frequently, when there is a perturbation, a gravitational perturbation in the vicinity of the solar system. These little chunks of matter that remain from the formation of the solar system fall towards the sun. And falling towards the sun, they are frozen, they are icy. We don't see them, they are very small, they are maybe as big as a mountain, so in astronomical distances, they are not possible, they are not visible from Earth. But when they come close to the sun, they get heated by the solar radiation, by the light and by the heat that emanates from the sun. And they start to emit gas and dust, and we see a tail forming, and this tail is what we see from Earth, is the comets. We call them comets. For many centuries, or for millennia, we have observed them and we didn't know what they were. Until only a few hundred years ago, we thought they were meteorological events, so something that happened in the atmosphere. We didn't even believe that they were happening in the skies. Only with the birth of the modern astronomy, we understood that these are these small objects that come from very, very far distant from the sun. And they're periodic, they come and they go, they come back. So we know that most of these comets are periodic. We can even determine their period. But what is important is that they are messengers from the past of the solar system. So we want to study them because it's like doing archaeology in space. We go and see how was the solar system before its creation. What was the matter that created the solar system? On the planets, this matter has changed because of gravity, because of the radiation of the sun. But these things, being so far away for billions of years, have been preserved. So we study them with telescopes. But since a few decades, since the birth of the space age, we can go there. We can send little probes, we can send spacecraft, interplanetary probes we call them, robotic machines that can fly in the vicinity of these objects and observe them. We did that for the first time in 1986. We took the first pictures of these objects from just a few hundred kilometers away. But then, recently, 10 years ago, one of our space probes, called Rosetta, landed on one of these objects. The nucleus of a comet of the size of 4 kilometers, so as big as the Mont Blanc, almost as big as the Mont Blanc. We managed to land on it. We collected an enormous amount of information about comets. And the scientists consider comets not only important because they show how the original matter of the solar system was composed of, but they have also theories that link them to our life on Earth, and in particular on two aspects. Did comets, for example, bring water onto the surface of the Earth? This was a quite widespread theory. It is still such a theory. The fact that the Earth as actually the only planet in the solar system has liquid water on the surface is a mystery. We don't know exactly why this happened. And it's very important for the creation of life on the Earth. So there was a theory, maybe comets have brought water. As you know, I'm not alone on stage today, so I would ask you to welcome on stage Telmo PIEVANI.
It was a great journey in the evolution of the universe, the planets, comets, and of our system. And evolution is a great journey as well. And if you consider time, the adventure of evolution lasted for at least 3.5 billion years. So it's a very long story. 3.5 billion years, it's almost a third of the history of the whole universe that Paolo was talking about. So now let's imagine, like in a metaphor, let's imagine to condense all this incredible amount of time into a single solar year. So something like a calendar of life, in a situation in which you have to imagine that all this time had passed from January 1st to December 31st. Okay? So imagine all this time condensed in a year. Each day corresponds more or less to 10 million years. And now we are right at the midnight of the last day, at the end of the year. Darwin, in his very famous masterpiece, The Origin of Species, wrote a wonderful sentence exactly in the final lines of his book. That was, from such a simple beginning, countless, most wonderful forms have evolved and continue to evolve. It's the only passage in which Darwin used the term evolution, transformation, mutation, change in life, in the cosmos, in the chemical elements, whatever. Evolution, change. So now we can start exactly from this very simple beginning, exactly when he hands down. As Paolo said, we don't know so far how evolution started on our planet, evolution of life, but more or less we know when it started. And we know that in the beginning our planet was completely inhospitable for life. It was a very infernal planet, as always happened in the beginning of life of planets, so very hot, rivers of lava, and bombing by asteroids and so on. So a very inhospitable place for life. But as Paolo said, something very mysterious and very unexpected happened. The surface of the planet has been filled out by water. Maybe from the inner part of the planet, or maybe from the outside, from outer space, so from comets. Anyway, we know that the primordial ocean atmosphere was formed very early in the life of our planet, so quite immediately after 4 billion years ago. So at that point, the stage was set. So stones, a lot of water, the sun, of course, so energy, circulating energy, and lightning. So energy, water, stones, mineral elements. But certainly we lack the ingredients, so the building blocks of life, as Paolo said. So amino acids, sugars, fats, acids, and other very strange molecules, very long polymeric molecules that were able, since the beginning, to duplicate themselves, that we call nucleic acids. As Paolo said, we know just that in the early stages of the universe, these kind of building blocks were still there, they were present. So now the ingredients are there, and so we lack the kitchen. Where was the kitchen? We don't know, because in science, it's much more, we have much more things that we don't know, and maybe that we don't know, rather than things that we are sure that we know. Anyway, the kitchen could be in two places. We have two hypotheses. One is a very famous hypothesis of the superficial soup, primeval soup, as Darwin wrote as well. And another one, so with the sun, with the radiation of the sun, with the situation related to the radiation of the sun. The other hypothesis is that life started in a completely different place, near to the hydrothermal springs, so in a completely dark situation, but with the heat of the internal part, with the geothermal heat from the Earth. Anyway, we know approximately that at that time something happened, something like fats producing membranes that were able to close it up, able to close within this something like bubbles of water, these ingredients that they were able to be interrelated, they were able to do metabolism, and so to eat something from the external part of the bubble and then produce bust. And in this case, they were able to increase their size, increase, and we think that some way, in a mechanical way, they started to be able to split into bubbles, and then two, and then two. And in each splitting, these molecules able to produce a reproduction, they were still there. So they were able to transmit this primordial, maybe RNA, or maybe already DNA, we don't know. So, now that we share more than 98.4% of our DNA with chimps. And I'm sorry, I have to say that you share more than 86% of your DNA with earthworms. Okay? And even, if you like, more than 45% of your DNA is shared with bananas. And with any plant that you can find in the planet. Because we are all relatives and all united by this wonderful journey of evolution. Okay, now it's time to talk about the future. We talk about past, present, the last seconds. Now it's time to talk about the future. And as Paolo already said, we always heard about the fact that climate always changed. Many denialists of climate change always say that, okay, climate always changes. But as Paolo said, there are at least two major differences between the climate change of the past. Even the climate change that happened in evolution, because climate change was important in evolution. Because for example, Homo sapiens migrated out of Africa due to climate change. So it was an adaptation to climate change. So climate change was crucial for human evolution. But the climate change that we observe today is much, much faster than the climate change of the past. Around 1,000 times faster than the climate change of the past. And secondly, the climate change of the past was caused by volcanic eruptions, great changes due to impact of asteroids, tectonic drift, or whatever, changes in the oxygen in the atmosphere, and so on. Now, climate change is produced by human activities, so it's a great difference. It's an anthropic climate change. So, in terms of evolution, what is happening? How can you imagine what is happening today and could happen in the future? In Germany, do you know beavers? Because in Germany there's a lot of beavers, right? Wonderful mammals, right? Wonderful rodents, beavers. And maybe you know very well the beavers' dams. Okay, beavers' dams are wonderful technologies, because maybe you know very well that it's a long story. It's very complicated to build a dams. You need weeks, and you need different materials. You need a strategy. You need the forms. You need a structure, and everything in beavers is wired in the genes, so it's incredible. If you try to domesticate a beaver in your house, it's not recommended. Anyway, you will see that in some precise moment of the year, the beaver in your house will begin to take every object and to produce a dams in your corridor, okay? Because it has the pattern of to build a dam. So it's wonderful. In evolution, we call beavers and other animals as ecosystem engineers. Why? Because they are able to change the world. Because beaver dams are able to completely change the streams, for example, of water in the mountains or in the forests. They create different habitats for other species, because they create ponds and small lakes, and so they diversify the habitats. For example, in a recent research in Bavaria, we observed that if you compare rivers and streams in which you have beavers and without beavers, where you have beavers, biodiversity is higher than more than a third, more than 30% higher the biodiversity with the beavers. So beavers are very good ecosystem engineers. Humans are exactly like beavers. Okay, we are beavers at the highest degree. We build dams in terms of technologies. You remember when we discussed about the cyanobacteria able to produce oxygen. So organisms are able to change the world, and then they have to adapt to a world that they change it. This is the game, dangerous and distancing game of evolution. And humans changed the world since the beginning, since the period of Africa, because we were able to go outside Africa, and in the archaeological record you clearly see that when Homo sapiens arrived, Homo sapiens changes radically the landscape, the number of species, the ability to move in the environment and to dominate environment. When the first humans arrived in Australia, they produced a mass extinction of the mammals in Australia, the same in North America and South America. So we are an invading species. We are a species able to change dramatically the environment. And even the Neolithic transition, so agriculture and husbandry, that today we think are the most biological and natural, the original attitude of humans. But if you look at them in evolutionary terms, agriculture was a radical revolution, because for the first time a species was able to domesticate other species and make ecosystem produce much more, a surplus of resources completely unexpected and completely unnatural. So
what if we, beavers out of control, do it really wrong and we bring this planet to a status where it's not habitable anymore? What if we ruin everything? We know this is the only planet we have. Do we have a planet B? Or is there a way to find it? I'm afraid the answer today to this question cannot be very positive, even for dreamers like us. Yeah? Then the first test case we have for a second planet to try is Mars. Mars is, to a large extent, very similar to the Earth. It's a rocky planet. There are not many, and the other two are pretty hot and inhospitable. It's a planet which has, surprisingly, the same rotation period. The day on Mars lasts 37 minutes longer than on the Earth. It's very similar. There's no reason for that. It's inviting. It has the same inclination, very close, the inclination of the rotation axis, which
struggling with the microphone. Wow, thank you so much. I mean, it was an honor for me to organize this show for all of you. So first of all, thank you for coming here tonight. We really appreciate it. And thank you to Paolo and Telmo for being here, to bring their expertise and their personality to this show. It's a really added value, and we are really thankful for this, so please a round of applause. I would like also to thank you, Marta Cametti, because you know, all the music that you hear tonight is originally composed by her, so it's all new, all played by Marta, so and of course, I'm not also alone in preparing all of this, because I would like to call also on stage Greta De Marco and Flavia Vigliotti that helped me a lot for this. As you may know, all of this was possible, and I really would like to thank you so much, the ESOC and the EUMETSAT Italian Cultural Club, but also the Italian Consulate, and specifically Massimo Darchini, the consul, the general consul. So thank you so much, and I would like to last but not least, also Michele Santoriello, that of course helped a lot in the organization, in all the process, and I would like to call him on stage, so please.